looking at is the product rule for derivatives. Now, to review something we've done before, just wanting you to see that it's just going to be slightly different from what we've done before to what we're going to do today in our lesson. What we've done before with regard to derivatives is we've done the sum of two derivatives on the question. For example, if I gave you the question was f of x is equal to x cubed plus 2x squared plus 5. Notice in this question we have a sum. There's three individual parts of this function, and then my job is to find the derivative of the function. How did we go about, Amelia, finding the derivative of a function like that?
So for x to the cube would be 3x. What's it? And then plus 4x. And then that's it.
And then that's it. Okay, so we did the derivative of each individual part of the question when we did the derivative of a sum. That will not be the case today when we go to do the derivative of a product. We cannot just do the derivative of each individual part. There'll be a formula that we're going to be following. It will involve doing a derivative, but it will also involve one extra thing that we haven't had to do before in our questions. You do not need to worry about writing the next couple things down. I just want to kind of show you again, just a slightly different example again with the sum. Then we're going to tie this example as well into a product in the question. So if I made, so we just did the individual functions, the individual parts, we did the derivative, we did the slope of each of those individual pieces to do the derivative of a sum. Go back, there we go. So if I made my original function, f of x is 2x plus 5. Anna, what is the derivative of 2x plus 5? It would just be 2. So the first part we drop a 1 down, so 2 times 1 is 2. That would give us x to the 0, so that disappears, and the derivative of a constant disappears, it's just 0. So the derivative, or the slope of the first part of our question is 2. Colin, what about this second function? What's the derivative of x squared plus 3x? So this is like the first time we rotated exponents down and then subtracted 1.
Okay. I'm just reading.
Okay, so let's start with the x squared. So we're going to swing the 2 down to the front, and then you subtract 1.
Oh yeah, so it would be x. It would be.
So if you move this down,
Yeah.
and then subtract 1 from what was currently there.
Oh, so it would just be 2x.
There you go. Okay, and then what about the 3x? Well, we do have the derivative, and that's the same as like 3x of course. So rotate that down, subtract 1.
This would be just 3.
It would just be 3. So the derivative of our second function, or the slope, is 2x plus 3. Now, Josiah, if I asked you to do the derivative of this question, so I added the two functions together, what would I have for the derivative of this function?
Would be 2x.
Yeah, 2x. And then what about your second part, the 5x? What would you
just be plus 5.
It would be plus 5, and then what about the plus 5 on the original question?
And then it would be 0.
0, because I don't have a variable, so that part would disappear on the question. So the slope, or the derivative of the sum, is 2x plus 5. Now, if you remember the original function that I had up there, let's get my note in front of me so I can write down my original function. There we go. The first function that I had given Amelia was 2x plus 5. The function that I gave Colin for g of x was x squared plus 3x. If I add those two functions together, that's where I got the f plus g that's at the top of the screen. There was nothing to add the x squared with, so that stayed as x squared. The 2x and 3x combined to make a 5x, and then we kept the constant of 5. The derivative of the first part of our question was just the number 2. The derivative of the second part of our question was 2x plus 3. Notice the final derivative of the sum is the sum of the two individual derivatives. The 2x has nothing to combine with, so that stayed as 2x, and then the 2 and the 3 came together to make a 5. So that's what we've done before when we had two individual functions and we had to find their derivatives. You just do the derivative of each one individually and then add them together, or you actually can add the functions together first and then do the derivative. You would have the exact same thing in your question. However, today when we go to get to the product, I do not do the product of the individual derivatives on our question. So we're going to have to look at how do I correctly do a product when it comes to derivatives. This is the format that we're going to be looking at today, so this is the first note. If you haven't written too much down yet, I need you to definitely get what's on the screen right now. So I'm given a function, but my function involves a product. And what does that mean, Josiah, that I have a product? It's what math operations are. Multiplication. Okay, so my original function is no longer an adding or a subtracting question. My original function is some sort of multiplication question. So how do I do the derivative when it comes to a multiplication problem? It is no longer just the derivative of each of the individual pieces like we just saw on the adding question. What we're going to do is, we're going to take the first function, the first part of the product, times the derivative of the second, so the second part of the product. Then we're going to add the second original function, that was the second part of the product, times the derivative of the first function, or the first part of the product that you had in your question. So when we go to do the derivative of a product, yes, we're still going to do the derivative of each individual part, but it's not just the derivative of each individual part. When I go to take the derivative of the first part of the function, I need to write the original second function next to that in my answer. When I go to take the derivative of the second part of the question, then I need to take the derivative of the first part of my problem. That was Colin's fault, Alyssa. Bless Colin. Alright, so we're doing the first function times the derivative of the second, plus the second function times the derivative of the first. So this is kind of like just a little notation as well. So f of x is the original first function that you have. So there it is, the first function. What is being multiplied by the first function? The derivative of the second. Okay, so it's always an original piece times the derivative of the second piece in the question. Well, I did the original first function. Now to start the second part, I need to do the original second function times the derivative of the first. Okay, and this is always going to be a plus sign here to start with. It possibly could rotate to a negative if one of the pieces that we have behind that is a negative number, because we know adding a negative does turn that into subtraction. We'll see an example in just a second as well that talks about differentials. Remember, with differential, all you do is you take the derivative, then you have to write like that dx or dy behind it, but we're still going to follow the same format. Take the first function times the derivative, or the differential of the second, plus the second function times the derivative, or the differential of the first in our question. Okay, just one more note, and then we'll work through a number of examples together this morning here. So this is, so if I'm looking at these two original functions in our question, if my job is to find the derivative of their product in the question, so I have to do f times g derivative. Okay, so that's kind of the format that we're going to see today in our question. According to the note that we just did, in order to find the derivative of a product, you take the first function times the derivative of the second plus the original second times the derivative of the first. Okay, so f of x is just the original first function. The original first function is 2x plus 5. And I'm going to put that inside parentheses because it has two pieces, and those two pieces need to get multiplied by the derivative of the second function. The second function is x squared plus 3x. Amelia, what is the derivative of the x squared plus 3x?
2x.
2x. And one more piece.
Plus 3.
Plus 3, because that technically has a 1 exponent. Rotating that down, 3 times 1 is still 3. Subtract 1, we have a 0 exponent, so that part disappears for the variable, so 2x plus 3. Plus, now it rotates. I'm going to take the original second function. The original second function is x squared plus 3x, and that's going to get multiplied by the derivative of the first part of our question. Colin, what's the derivative of 2x plus 5?
Would be 2.
It would just be 2, okay? Because this technically has a 1 rotated down. 2 times 1 is still 2. Subtract 1, our x disappears, and the derivative of a constant was always 0 in the question. So I'm taking the first function, derivative of the second, plus the second times the derivative of the first in our problem. Everyone with me so far? What's happening in our questions? Alright, so now it's just a matter of simplifying this question and then combining our like terms. Anna, can you help me on the first part of the question, foiling the 2x plus 5 and the 2x plus 3?
4x squared plus 6x plus 10x plus 15.
Good. And Josiah, can you distribute on the second part of our question?
2x squared plus 6x.
Okay. And then Amelia, will you finish by collecting the like terms together?
6x squared plus 22x plus 15.
There you go. So there is our final answer for the derivative of the product. Notice again, I did not just take the derivative of each individual pieces, then multiply them together. That is not the correct way for the product. That was the correct way for the adding. With the product, the first function times the derivative of the second, plus the second times the derivative of our first in our question. All right, let's go ahead and work through some different examples together. So actually, I think I have most of that written out, but that's okay. And then you get something good. All right. Okay, so that's just with our differential. We'll see it again. It's just the first differential, second differential first as well. All right, here's our first function. Y is equal to x squared sine x. Now, what's going to happen on a lot of our questions is not going to say, okay, here's f of x, here's g of x. The product appears as one original function. So when it says x squared sine x, recognize that that's x squared times sine x. So there's the product. My job is to find the derivative of y. That's the name of the question that I have up here on the screen. So how do I do a derivative? I take the first function times the derivative of the second to begin. What is the first function that I have on this question, class? The x squared. So the first function, I copy that right down, times the derivative of the second. The second function that I have is my sine x. What is the derivative of sine x? It was cosine x. Then I drop in a plus sign. We're always going to put a plus sign to begin with. Now behind the plus sign, it rotates. I do the second function times the derivative of the first. What's the second function in my question? Sine x. And then what is the derivative of the first part of my question? 2x. Final part of our question, just neaten this up. X squared cosine x. Well, I can't really multiply those together, so I just simply write those side by side. I don't need those parentheses anymore. So x squared cosine x plus. Same thing over here on the right-hand side. Those aren't like terms for me to be able to combine it together. I'm just going to put the 2x first. So I have 2x sine x, and there's my final answer for the derivative of our product in our question. Okay. Any questions on that first example? Everyone understanding what we're doing? We're going to take a quiz on this tomorrow, so in case that inspires you to questions on that first example? All right, let's go through our other ones here. So here's our next function. So again, it's just called f of x. Don't think, oh, f of x, that's just one function. I need to have a g of x. Yes, it could be presented like that. But again, notice that our original function is a product. It's x squared times ex when they're side by side. So how do I do the derivative when I have a product? I follow the pattern, the original function times the derivative of the second, plus the second times the derivative of the first. I begin with the original first function, and that is my x squared, times the derivative of the second. What was the derivative of e to the x? E to the x. That was the one function that we had. Its derivative was itself. Plus, and then it rotates again. Now it's the second times the derivative of the first. The original second function is my e to the x. What is the derivative of the first part of my question? 2x. All right, so let's neaten that up. We have x squared ex plus 2x ex. Now, there's nothing wrong at all with presenting the answer like this. Our textbook on occasion does write it in a little bit different format by factoring. What do you notice is contained between these two parts of our question? What do they have in common? They both have an e to the x. Is there anything else that they have in common? So it's not exactly the same, but there is another common factor between those two pieces.
You can pull out an x.
You can pull out an x. The first one has x squared, which means it has two x's. The second one just has an x. So there is a common x that I can take out to the front as well. If I do that, that would leave me with just an x from the first part of the question, and it would leave me with just a 2 from the second part of the question. Again, that's not absolutely necessary. Either one of those answers would be considered acceptable. So if you want to stop right there, that's okay. But sometimes our textbook does factor some things out to the front that they have in common. All right, let's go to our next question here. Okay, so it calls u is my first function, that's ln x. V is my second function, and that's 2e to the x. And then over here, it just defined the product for me. The original problem wasn't written as a product, so it's defining the y question as u times v. So if you wanted to, if it helps you to see it, you could say y is ln x times 2e to the x. And if that helps you to think through the question, then do it like that. All right, so how do I find the derivative of a product? It's the first function times the derivative of the second. What's my first function? ln x times. What is the derivative of 2e to the x? 2e to the x. E to the x, its derivative was itself, and we can keep the 2 in the front. Plus, rotates. Second function times the derivative of the first. The second function was 2e to the x times. What is the derivative of ln x? So it was what? It was 1 over x. So that's when we did a reciprocal when it came to our ln function. All right, so let's tidy this up a little bit. We have ln x. Actually, let me write it better like this here. Let's put the 2e to the x first, since there's a coefficient. So 2e to the x, ln x, plus, and let me write this like this currently, because I'm going to do one other thing in this question. What do you notice that both of these questions have in common? The 2e to the x. Again, if you wanted to stop right here where I just left off, that's perfectly fine. You could, if you wanted to, put the 2e to the x into the numerator and write 2e to the x over x for the second part of the question. But again, on occasion, the textbook does factor. They both contain a 2e to the x. So yank that out to the front. And then this is the way that the textbook would present the final answer, but I'm perfectly fine if you stop right here, or even if you move this up to the numerator as well in your question. Okay, are we good so far? I'm doing our products. Thought this would be a good lesson for us because you guys were good at doing different derivatives. All right, 2 more examples, and then we're done with our lesson. We'll work on some of our homework questions here. We mark with that one. Okay, let's go to this question. So the s function is x squared y cubed. Then it says find ds. Now this notation right here, ds, is that a derivative? No. What is that notation when it said ds? Or sometimes we saw it dx or dy. It was a differential. Okay, so with the derivative, usually we saw the prime symbol, like we've seen so far, y prime, f prime, x. When it says ds, that's a differential. Well, to do a differential, it's the exact same formula. There's one thing that a differential does include that a derivative doesn't include, and we'll see that as we're working through our example here. So how do I do this derivative of the s function, because the s function is a product? Same pattern. I take the original first function. What's my original first function? X squared. Times the differential now, instead of the derivative. Okay, so how did I do a differential? I began with a derivative. So what's the derivative of y cubed? 3y squared. What else do I put behind the 3y squared because I had a differential, not a derivative? It was not dx. D is not ds. It's dy, because that's the variable that I just worked with to do the derivative of the second part of the question, so I put a dy. So this y is y, we put the letter y behind the d. So dy is the differential with respect to y. That was the variable for that part of the question. We got our plus. Rotate. What is the original second function? y cubed times no longer just the derivative of the second, the derivative of the first, but the differential of the first. So how did we do a differential? We began with the derivative. What's the derivative of x squared? 2x. And then because I'm doing a differential, what needs to be behind that 2x? dx. So this one is a dx because we just did the differential for the x. What is the variable this time? Okay, everybody with me? On the differential, same pattern, just put in that dy, dx, dt, whatever variable you're working with. Let's just neaten up this question to give our final answer. I'm going to put the coefficient first of 3. The order of the variables doesn't matter. I'm just going to go alphabetical order. X squared, y squared, dy. So the dy does not need to stay directly attached to the y squared. As long as it's anywhere within that part of the function, that's perfectly fine. Do the same thing on the second part of our question, coefficient first. And again, I'm going to put the variables in alphabetical order. So my x first, then my y cubed, then I'll finish with the dx. Now, what's actually interesting here, when I was looking at the examples in the textbook, they never factor for the differential. Why all of a sudden they stop? Because these do have some things in common. They both have an x, they both have a y squared, and I guess if you wanted to, you could, but I would just leave it in the unfactored format. I would give this as my final answer in our question. Okay, let's see if you guys can do the last example for me. Here is my function. See if you can find the differential of y. Again, this y is because the original function was called y. The last question said find ds because the original function was s. Then I just move the 2s out to the front, so I have my coefficient and variable first. Again, the order technically doesn't matter, it just looks better to have a coefficient first in your question. Are you guys able to come up with that final answer? Or any questions on how I got that? Yes, sir?
Do you have to move your S up with the 2, or can you just move your 2 to the front?
You could just move the 2 to the front, that's fine as well. Usually I try to put like coefficient, variable, and then if there's any like e to the x or trig part, that's how I end the question. Because if I put it behind it, it almost looks like I'm doing the sine of ts, and I'm just doing the sine of t. That would be my only issue with that. But if you left it back there and I can see that's what you're doing, that's okay if you did have it back there. Anyone else, any questions for me? Alrighty, let's go ahead and look at our homework that we have for today. You guys have about 10 minutes that you can work on that. You'll be able to get these questions done for me. We are on page, let's see here. This is page 172. I would like you to do questions 3 through 6. And actually, let me change that. It's 3, 4, and 6. I just saw question 5, just slightly different. So let's go 3, 4, and 6. Questions 3 and 4 is just the derivative. Question 6 is the differential. So that's page 172, 3, 4, and 6. 3 and 4, just derivatives. Question 6, differential.